It is snow day time. So, since we have snow day things going on, and I'm not 100% sure how the university is going to do things in terms of making up the Thursday lecture, because presumably Friday will have lecture, so that section will have one extra lecture compared to the Thursday section, and the Thursday section would miss their tutorial. So what I'm going to do to try to mitigate some of the potential issues there, make things go a bit smoother, is I'm going to build digital lectures for lecture 18 and for the tutorial that would be missed today. And again, I'm not necessarily at this point in time expecting people will necessarily need to watch these. This is just here to try to make things more smooth and less disruptive. Okay, so lecture 18, what we're going to do is we're going to solve initial value problems again, but now we're going to have different types of forcing terms. Instead of having things like these nice sine, cosines, exponentials, polynomials, we'll have forcing terms. Our forcing terms will be functions that will be called piecewise continuous, or are said to be piecewise continuous. It's so awkward doing video lectures. Anyways, here's the idea. In electrical engineering in particular, you often want to have a forcing term that turns on for a while, right? And then this forcing term turns off at some point, right? This is not a continuous function, but if I still try to take my f is equal to ma, right? Remember that the acceleration is the second derivative. I could actually solve this differential equation here with a forcing term that looks like this. I integrate twice, and what ends up happening is this discontinuity kind of gets smoothed over, right? So the second derivative of my solution will be discontinuous, but the first derivative and the function itself will be nice and continuous. So in this case, if you actually just integrated this guy, you could actually see what the solution was as a function of time, and obviously, like, you do your standard integration stuff there, right? But at a deeper level, what we really want to do is come up with a nice systematic way of solving our general equations. So these guys plus our alpha y prime plus beta y is equal to forcing term. We want to solve these kind of problems where the forcing term is allowed to look something like this, or more complex functions, right? I could do oscillations, and then at some point I go to 0 for a while, then I go back to oscillations. Yeah, the types of signals you would imagine going in and out of a circuit, kind of thing. Okay, so we'll switch over to our kind of standard math stuff here. So here I'm given a function, given the definition for a piecewise continuous function. The idea, so just ignoring the formal definition for a bit, the idea is that a piecewise continuous function is not necessarily continuous, but it's kind of continuous. So for a piecewise continuous function, there'll be a number of points. So here I'm just picking 4, where the function is allowed to have a discontinuity. So this is kind of my point 1, finitely many discontinuities here. And at each one of these discontinuities, what I'm going to do is I'm going to force that the solution, or that the function on either side of it does something kind of nice, right? It has a limit. It's not diverging off to infinity or anything like that. It's just like a well-behaved function, right? And if I have a function that does this, so it has some points where it's bad, where it's discontinuous, but at those points the limits exist, and away from those points the function is itself continuous, we say it's piecewise continuous. All right, so here's 2 kind of classic examples. You want to check both these conditions. So for f of x, what we're going to do here is we'll just plot it, because the plot has a nice visual aspect to it, obviously. So here, that's what my function looks like. It has one discontinuity. The discontinuity is right there at the origin, right? But at that discontinuity, the limit as x goes to 0, either from the positive or negative direction of 1 over x. This thing is either infinity or it doesn't exist, your choice, right? But it doesn't have a nice finite value, so this function f would not be piecewise continuous because of that essential singularity, right? So we have to have these limits exist. Infinity isn't existing. Now, for our other function, what we're doing here is at 1 and -1, it changes branch, right? And if I am bigger than 1 or less than -1, then I look like my 1 over x function. So since I had this inequality here, this guy gets my circle, and I get this. Over here, I've got a little circle, and I get this. And in the middle, I have solid line, 0, solid line. So here, the limits on either side of both of these discontinuities, the one-sided limits both exist, right? And the function is continuous everywhere except for these two discontinuities here and here, right? So this guy would be also piecewise continuous, right? So not, this is. I would say any questions, but yeah. So the next idea, and this concept is more important later when we start talking about Fourier series. This idea of piecewise continuity can be extended to talking about derivatives. So I can talk about a function being piecewise C1. To be piecewise C1, effectively, I need to have the derivative existing on a bunch of intervals. So all the spots that are excluding these discontinuities, I have a derivative, and the derivative is continuous. So it's like piecewise continuous, but I'm really just asking about the derivative instead of the function itself, right? So again, we can analyze these to check if they're going to be continuous, piecewise continuous differentiable, or piecewise C1. And these concepts are slightly related, right? Like if I am differentiable, then I'm continuous, right? Between these two, there's, if I'm continuous, I'm piecewise continuous. But if I'm piecewise continuous, I'm not necessarily continuous, right? So there are some like simple relations between these four concepts, and we'll try to illustrate some of those by examining these four examples. So here, my pro tip for doing these is you could analytically try to check, is it continuous? Can I take all the limits? Is it differentiable? Evaluate the difference quotient. That becomes necessary for some of these computations. But for the purpose of ECE 205, we can just plot this guy. If I plug in 0, I'm up here. Absolute value gives me a slope. I do this, I do this. There's my little cartoon picture. If I look at it, this one is continuous. It is also piecewise continuous, right? Continuity will always imply piecewise continuity, not necessarily the other way around. But yeah, it's piecewise continuous. It has no discontinuities, and it's continuous, therefore, yeah. It's not differentiable, right? And it's not differentiable because of this kink right here, right? There is no well-defined slope at that point, if you want to think of it that way. But it does happen to be piecewise C1. Right? And the reason why it's piecewise C1 is I can just do the check. Right? So if I were to take this guy and actually plot what its derivative would be, here I get a positive slope of 1 coming from the absolute value. So I get this guy, and then that fails to hold at the point 0, and now I have a downward slope at -1. Yeah. So the function, the derivative is defined everywhere but 0, right? So it's continuous on all these intervals. So it's continuous from -infinity to 0, 0 to infinity, right? It exists, continuous, and it's bounded on all those intervals. It's either -1 or 1, right? So because of this, this guy's going to be piecewise C1. Okay. Now we can do the same thing for this h function. So all I'm doing for h is I'm breaking continuity, right? So the Heaviside function, remember the Heaviside function's the thing that does this, right? This is my u of x, not u of t anymore. So if I actually plot this guy, it's going to be 0 here. Then when I have my little open circle, my closed circle up here, and then it's going to go down like this, right? So this guy is not continuous anymore. Right? It's not continuous because of this discontinuity, but it still is piecewise continuous because it's nice and continuous on this interval over here, and it's nice and continuous on that interval, and these limits exist, the one-sided limits, of course. It's also not differentiable, right? But it is piecewise C1, right? So if you're differentiable, you will be piecewise C1, but not necessarily the other way around. And again, here's where I would normally ask for questions, but video. Okay, so now I'm going to wipe this, and we'll do it with G and L. So for g of x, we can do the same thing. You can just plot the function. This one's a bit trickier. Right? At 0, I still have 1. And if I think of what x to the 2/3 looks like, right, its limit as x goes off to infinity will be infinity, but at 0, just this term will have basically like a square root type behavior. So this guy's going to look like this kind of thing. So if I do 1 minus it, it's going to be this but flipped, right? So this guy is going to go like this and diverge off, and it's going to go like this and diverge off, right? So this, if I just look at it, it's continuous. It's also piecewise continuous, right? Because it is continuous, but it's actually not going to be differentiable, right? Just like the previous one where I had this kink point up here, so it's going to be not differentiable. Now when I ask about piecewise C1, I actually want to compute its derivative to see what its derivative would look like, right? I'm just going to do this geometrically, but formally, you could take the derivative and see what happens. Here, if I look at these slopes, right, here the slope's positive, and as I get closer to 0, the slope starts increasing. So this guy, the slope's going to look something like this, and if you take the derivative, that would be your x to the negative 1/3 with some coefficient in front of it. That thing's going to blow up there. Now here, I start negative, slope's going downwards, right? Starts negative infinity and goes here. So here, this guy, in this region, my derivative is not bounded, right? So over here, derivative exists, derivative is continuous, but I'm breaking this point, right? So this guy is not bounded. Obviously, if the function's not bounded, the derivative is not going to be bounded as well, given that it exists. So this guy is not piecewise C1. Yeah. And then here, this is basically for the L. It's doing the same type of problem. I'm 0 here, open, solid circle here, decay down the same way over here, right? This guy is going to be not continuous, but it will still be piecewise C1, or piecewise continuous, not piecewise C1, because these limits exist. It's all well defined. It's continuous on either of these halves, so that's all good. It's not going to be differentiable, and it's not going to be piecewise C1. Yeah, so you can take from these examples just kind of the classic types of behaviors that you can expect from these different types of functions. And effectively, what we care about is, for now, this is going to be the type of forcing term we look at, the piecewise continuity. This is something we only need to define the next definition that we're going to do. And it will come back when we do Fourier stuff, though. So kind of a stepping stone. The general definition is piecewise Cn. So for piecewise Cn, you basically need your derivatives to exist on the intervals, right? In order for Fn to exist, I need the previous derivatives. So let's talk about the biggest derivative. I need Fn to be continuous, and I need all the previous derivatives from, well, technically 0 up to n. I will update that. But we want all the derivatives from the function itself all the way up to the nth derivative to be bounded on those intervals, right? So if I say piecewise C2, I'm basically saying I have a function that it might not be continuous, but where it is continuous, I can take two derivatives, and its second derivative would be continuous, excluding the points where I have the original discontinuities of the function, right? So that's the idea here. And we care mostly about the case of 2, but if we're doing it for 1 and 2, might as well just do it for n. Okay. So now the nice thing about this particular unit, right, when I'm dealing with these piecewise continuous forcing terms, so again, forcing terms that look like this, it can be really annoying. It actually is pretty annoying to do this manual integration type stuff. And it gets even worse when I'm dealing with the equation like this one over here, right? If I'm dealing with this equation, it's just, you have these conditions where you actually have to make sure that the function you're finding agrees on these intervals, basically coming from different constants of integration. So it's kind of annoying to actually make those match up. So lucky for us, we have this formula down here that we derived, the time shifting formula, that allows me to compute Laplace transforms of things that turn on and off with the step function. And it also turns out that all these piecewise continuous functions can be written as a weighted sum of Heaviside functions. So if I put these two things together, I can solve these equations with the piecewise continuous forcing terms by doing the Laplace method and literally just reading things off the table, just like we did in the previous lecture, right? So it's quite convenient for us that we can do this. It's also kind of nice for me, so I don't have to teach the continuity conditions for actually stitching together the little pieces of solutions for these kind of equations, right? Here, that's not an issue because you just integrate, but here you actually solve the DE on, well, we'll just pick this one. You solve it here, you solve it here, and you solve it here, where the information from this solution feeds into the initial conditions for this problem, which then feed into the initial conditions for this problem. So that's kind of annoying. So I'm glad we don't have to do that. You should be too. So that's what this theorem says. So all piecewise continuous functions can be written as a weighted sum of Heaviside functions. We're not going to prove it, but instead we're just going to show the concept, right? So to be piecewise continuous, I have to have, back over here, a finite number of finite number of discontinuities, right? That's kind of key. So if I show how this works for, say, like 4 or 5 discontinuities, you can see how induction could be used to actually do the formal proof of the theorem. So to do this, we're just going to look at this example here. So what I want to do is I want to write f of t by turning functions on and turning functions off at the appropriate times. So 1 is my first branch here. So I can just say, well, I'm going to start with f of t is 1. And this is valid, like this particular statement here is valid for t is less than 0. Right? If t is bigger than 0, then this is wrong. Right? So if t is bigger than 0, what I want to do is I want to use a Heaviside function, u of t minus 0 technically, and I want to use this guy to turn on the 2 term and turn off the 1. Right? So here, if I do 2 minus 1, this term takes 1 and it turns it off, right? Because I have a negative, so 1 off, if you will, 2 on. And effectively what's happening here is I get 1, then when t is bigger than 0, I get 1 minus 1, which goes away, and then I get my plus 2 to give me the 2, right? Now, if I just repeat this for the rest of these, so pi and 10, then I can get the full form, right? So now, this works until I get to the branch below this little box, right? Until I get to the sine term. So to turn the sine on, oops, not sine, to turn the sine term on, I want t minus pi, right? So this guy is going to be 0 until t is pi, and then it's going to pop up here and turn on, right? So here I want to turn off the 2. So this is the 2 turning off, if I put a negative in front of it. And here I want to turn on the sine, so I get sine of 2t. And that's kind of scrunchy, but there you go. So we get this. So this is 2 off, this is the sine on, right? And then finally, if I want this last term, here I'm going to want to turn my e to the negative t, cos of t, on, and I want to turn this function off, sine of 2t. And then this wants to happen when t is 10, so u minus 10. Okay. Now, in terms of this breakdown, one issue you might see is here I designed the question in such a way that these inequalities were all compatible with the way that we wrote the Heaviside function, right? But you could say, well, what if I were to change this inequality here to be that's the not equals and this is the equals case? Then technically this doesn't work because I'm missing a point. But for the problems that we're working on, we care about integrating things, and integrating a function, well, a single value of the function doesn't actually change what the integral is. So this distinction of which one is equals, where do I put the, just going up here, where do I put the closed circle? Is it over here or down here? That doesn't actually matter, right? So that's one thing to keep in mind. You might see some cases where these are flipped, right? And then this theorem, well, you have to redefine your Heaviside function to allow for that one point. There's a function that does it. We'll do things with that later. But yeah, so this guy, you'd have to modify a little bit if I don't write the functions of these forms, but that's just a very minor semantic difference there. Again, this is the point where I'd ask questions. That's so ingrained. Anyways, so let's go on to theorem. Okay, so this is kind of our big theorem for existence of things. It's important from a mathematical perspective because it tells you that there are theorems. For us, we're not going to prove it. We're instead just going to run with Laplace. So effectively what it says is if I give you a linear difference equation with constant coefficients and a piecewise continuous forcing term, then all initial value problems of the standard form, so standard initial conditions, have solutions, and the function that I find is going to be piecewise C2. So here, this is actually typo that I will fix. So that function will be piecewise C2, and these two functions, y and y prime, will be continuous on the interval from 0 to infinity. Right? So it's just our nice little existence theorem. Like once I integrate these things, it'll behave well. The essential idea of like the basic idea of the proof is if I ignore these terms, which is obviously not the general problem, but if I remove these, if I integrate this twice, obviously when I integrate, that function would be piecewise C2, right? When I integrate a function, even if it has discontinuities, it's now continuous. And because I integrated it, obviously I could take a derivative of the thing that I get after integrating by fundamental theorem of calculus, right? So that's the basic idea. And I'll go fix that oopsie now. Yep, there we go. That typo's fixed. Now it's just the y instead of the y prime, or y double prime. So we'll end this lecture just by solving a differential equation, right? So if I give you this is something that we've seen similar problems before, but we haven't seen this exact question. The key difference is here, I think we saw this exact problem if this was sine of 2t, but now the sine of 2t signal is turned off for a while and then turned on, then turned off, right? So basically you have a system, like some type of pendulum system or a RCL circuit. You have no input signal for a while, you turn it on, then you turn it off. What happens to that circuit? Yeah. So in terms of a RCL, this one has no resistor, so energy just propagates forever. In terms of like a pendulum or a spring problem, I have no friction, right? So here, all I want to do is go find the system output. So we haven't dealt with these type of things before, but we have a nice little Laplace table that tells us how to take Laplace transforms of Heaviside functions, right? So we can just simply use that. So here, I want to write f of t as a sum of Heaviside functions. So here, because this is kind of a sine of 2t's being turned on at this point and turned off at this point, I can just think of it as this is sine of 2t times, I want a function that goes 0, then at pi over 2, it jumps up to do 1, and then at here, at 5 pi over 2, it jumps down back to 0. Right? So I want a function that does this, and I can do that using my Heaviside functions. So to turn this on, I do my u of t minus pi over 2. All right? This function would 0, and it stays on forever, so it does this. All right? Now I want to turn it off, so I can subtract off a Heaviside function that basically starts at this point. Right? So I want to subtract off, if I draw it up here, the Heaviside function that's 0 and then jumps up, right? So this would be u of t minus 5 pi over 2. Yep, that makes sense. So these guys together give me this hat. So it turns off, turns on, boop, and then this term stays on forever, but this one turns on here, so I now get the cancellation at this point to drop it back. Yep. So with this, with this in mind, now all I have to do is go to my Laplace table and treat this like any of the problems that we've done over the last lecture and a half kind of thing. So here, if I take the Laplace transform of the whole dE, y double prime gives me an s squared y of s. And actually, before I continue, since it's a video lecture, you might want to try taking this Laplace transform on your own first, see if you can do it, and then you could follow along kind of thing. But anyways, this guy, I get this, minus s little y of 0, my initial condition, minus here my y prime of 0, plus, now I'm going to get 4 times my just capital Y of s. All right, Laplace transform of y is Laplace transform of y. This is going to be equal to Laplace transform of this whole thing. So I'm just going to write it out here. Back in the COVID days, I would put fun music over the thing, but I'm not going to make the fancy editing here because that's a pain. T minus pi 5 pi over 2 over 2. So this black on blue is kind of bad, but this is that function. There. Okay, so now I want to simplify this thing out, but to simplify it, I really need to compute these Laplace transforms, right? So let's just do the low-hanging fruit. This guy is 0. This is 0. So the left-hand side becomes s squared plus 4 y of s is equal to, here I can use linearity to split this up. So I could say this is going to be Laplace transform of sine of 2t multiplied by my u of t minus pi over 2. That's the turning on of the sine function, if you will, and then the turning off of the sine function. So sine 2t u of my t minus 5 pi over 2. I also really hate how this editor, well, not really, it's just drawing in PDF. I just really hate their style of splines here because it makes my horrible handwriting even worse. Okay, so now I really need to go compute these transforms, right? Now I could do this by compute this one, do it in parallel, or I could be a little clever here and I could think, well, all I really need to do now is actually compute a general transform, sine of 2t, Heaviside of little t minus capital T, where my capital T is bigger than 0. All right, this is fundamentally, if I compute this, then I've got both of these cases, right? I just changed the value of capital T. So by being clever in this way, it makes things pretty nice, right? So I'm going to pause video and pull up our Laplace table just so you can see how to do it with the table. Okay, and we are back. Here's our little Laplace table, right? We want to compute the Laplace transform of this, and we see that we have a rule for doing it here, but we don't have our function quite in this form because what we would actually want is our sine of 2t to look like to have the t replaced with the t minus a t, right? So since our forcing term isn't compatible there, we need to turn around and make it compatible. And the way that we can do that will depend on effectively what t is, right? So for negative pi over 2 and 5 pi over 2, I can introduce this shifting factor, which would then just modify sine into cosine, negative sine, things like that, just because these are nice trig numbers. If they weren't particularly nice, then what I would end up doing is just the general transform. So I'll show it in the general transform, not having the nice numbers, and then we can plug in the numbers to see where things become nice for this particular problem. So the rule is this guy, Laplace transform becomes this, so I can pull out effectively, if you will, this e to the minus st, so in this case, e to the minus s capital T for the general formula. But if I do that, I then get the Laplace transform of the thing that I had here, so sine of 2. I had t minus t, and I want t minus t to turn into just a t, so this is going to get me t plus the t. Yeah, so effectively what I'm doing when I pull this guy out, when I pull the Heaviside out of Laplace, I'm adding t to my t, right? So this is the general form, right? And notice we don't actually have a Laplace transform here for a sine of 2t plus t, right? So now we either need to go to first principles, where we figure out like what happens if I give you not a pure sine or a pure cos, and there's trig identities you can use to simplify that out, like the sum identity in this case, right? Or we can just plug in our values here. So we're going to actually plug in the values and see how things simplify. So in our two different cases, if t is my pi over 2, that was my value, right? Yeah, if my t is pi over 2, then what I really want to deal with is the sine of 2t plus pi over 2, right? But this simplifies to just sine of 2t plus pi, right? And here, when I add the pi to the sine, I just get a negative sine of 2t, right? So in this particular case, if I plug in my pi over 2, this guy becomes the Laplace transform of sine of negative 2t. That's now something in my list. Yeah, and I would do it for the other one. So I am going to pause, clean this up a little bit to make it look nicer, and then come back. Okay, full screen mode. Now we have this guy here. So in this case, my Laplace transform of my stuff, the stuff being the sine, will become e to the minus s pi over 2 times negative sine, negative Laplace transform of my sine of 2t. Sine of 2t, it's one of the common ones in our list that we totally should memorize. That's more common for you guys. Pi over 2, this guy's going to give me a 2 over my s squared plus 4, right? Like, you will get the list, but it's nice to have it there. Okay, so this is dealing with this first term, right? So here in this ODE, this whole term I'm boxing in now will simply become this guy written here. Now, I need to do it the same computation in the case where t is my 5 pi over 2. Right? So the similar computations here, I'm going to end up with my sine of 2t minus my 5 pi over 2. Oh, so horrible. I apologize for the bad writing. Yeah. Notice from here, if I actually plug this in with the plus, there we go. If I actually plug this in, I'm going to get sine of 2t plus 5 pi, right? 5 pi is going to get me the same negative sine of 2t. So I'm going to get a negative sine of 2t as well. So when I go to take my Laplace transform on this, I'm going to get a similar expression just with this guy shifted, right? So here I'm going to get my e negative e to the s 5 pi over 2, so bad, times my 2 over s squared plus 4. Okay, so if I put these all together, the only difference between these two terms is that this one is going to get a e to the negative pi over 2 times s. This one's going to get an e to the negative 5 pi over 2 times s. Right? So if I put these together, right, so that's how to use this one rule that we derived, right? The time shifting rule. So yeah, just like all the other rules, you just make sure you don't have typo kind of things. So if I put all these together, now what I actually have is my dE, this s squared plus 4 y of s, s squared plus 4 times my y of s is equal to, here, both of these are going to have my negative 2 over s squared plus 4. Right? This guy has a negative, that guy has a negative. Here, I'm taking this one minus that one, so I'm going to get my e to the pi s over 2 with a negative minus my e to the 5, negative 5 pi s over 2. Right? So just by symmetry of the problem, they're both still going to be these nice sine waves. If we modified these to not be these values, then these sine waves could turn into cosine, or you could do some identities to modify it into a different amplitude sine and cosine, like we did in the harmonic oscillator lecture. Right, so that's generally where you need to use that formula. I will give you things to try to avoid using that formula. So now what we need to do is solve for y of s, which is pretty straightforward. Y of s is going to be this guy divided by here, so I'm going to get my resonance going on. Yay, yay resonance. I'm going to get my minus 2 over s squared plus 4 quantity squared. Here I'm going to get my e to the minus pi s over 2 minus my e to the minus 5 pi s over 2. Okay, so now what we have to do is we actually have to go through and compute the inverse Laplace of this guy in the box. Dealing with the exponentials are pretty trivial, right? I just unpack it, right? So here I have e to the negative st. So if I know what the Laplace of the box is, I can use my shifting formula, the backwards direction, to introduce my Heaviside and to just shift my function, right? So most of the work here, pretty much all the work, is figuring out what the inverse transform of the box is. And we've done this before, right? The general ansatz we're going to make is that the thing in the box is going to look like, well, let's look at my list and see what we have, right? Just to derive it instead of just telling you. Here, this is the closest thing in the box to this, right? But the difference is, this part, I need it to be squared, right? But it's not squared. So it's not exactly this. Now I have to look at my list to see where I could introduce something that could force this to be squared. Linearity won't do it, right? Because it just lets me separate out sums and pull out coefficients. Time scaling won't do it because the issue isn't having s divided by a number, right? I have my legitimate s. If, for instance, this was s over a squared, then I would do my time scaling. Exponential modulation, that just shifts in the time domain. I don't have a shift, so it's not that. Time shifting, well, it's not going to be that because our time shifting is actually dealing with this term. So the only real option left is multiplication by t, right? So what I notice is that if I want to get a squared, if I take the, I can't write here, but if I take the time derivative of, or sorry, this s derivative of this, that will give me a square in the denominator, and then I just have to make the rest of the ansatz so I can actually solve to do that breakdown. So the guess that you're always going to make here is going to be negative. Negative because I'm using here, and there's a negative in this formula, and I'm doing a first derivative. So just highlight it. So negative, the s derivative, because I only need one to get a square, of, I don't know whether it's going to be sine or cosine, right? So I don't know how the cards are going to lie there. So I'm going to make it as plus b over my denominator, s squared plus 4, not squared, because when I take the derivative, the quotient rule will force this to be squared. Now, that would be wonderful if I could solve the problem doing this, but in general, I can't, because that's not the right partial fractions decomposition ansatz, right? Normally, I would have one for a square and one without a square, so I have to add back in a cs plus d over my s squared plus 4. All right, So this is kind of my standard partial decomposition ansatz, but I replaced what normally would be as plus b over s squared plus 4 quantity squared with this derivative form. Now I can do some cleanup to make it even nicer. If I put a 2 here, this 2 is now compatible with having my omega squared and omega. Omega squared is 4, so I want a 2 in front of the constant coefficient. And I can do the same thing here. Right? So if I put a 2 multiplied by the b. Yeah, so this is the best ansatz you could set up for this. And if you do this ansatz, you now actually go compute this derivative, right? And then you can do Heaviside cover up to get a and b. Then you do the trick that we did in class where you pick random numbers. Here, picking like 0 would be a nice number, and picking 2 would be another nice number. But you just pick some numbers and you can solve for c and d. If we do this, we get a is a fourth, b is 0, c is 0, and d is negative an eighth. Okay, so that's just after you compute this, literally take its derivative. It's a nasty little expression. It will be uploaded in the answer that's uploaded, but it's a nasty little thing. You then just plug in, use your Heaviside method, and you get these. Yeah, and again, Heaviside will not access this, because to access this part, I need to multiply by s squared plus 4, but I still have a s squared plus 4 left over, so obviously I can't plug in my 2j to make that 0, because I would divide by 0. Okay, so now that we have this, this is how to actually compute the Laplace transform of this piece. Then I just do the modulation. So let's do that, put the pieces together, and be done with the lecture. So here, my Laplace transform inverse of, I'm going to zoom out a bit. Actually, I'll make this full size here and then zoom out a bit. Of this guy here, my minus 2 over s squared plus 4 quantity squared. This will be equal to my 1/4. So this piece here, the a is associated with this guy. This, from my Laplace table, will be t times cosine. So we get t cosine of 2t. Right? T is dealing with, is it going to let me change color nicely? Let's try. Oh, okay. So the t is dealing with this stuff, right? So that's what the t does. Oops, there you go. And the cosine is dealing with the bit in here, right? Plus, or minus, an eighth times, the eighth came from this coefficient. This guy's going to be my sine. Sine of 2t. Okay, so that's the Laplace transform here. Now, just because this part's the new part for you guys, if I want to do my time shifting, so I'm going to use this rule again. Let's unhighlight and highlight this. Yeah, so now I use this rule to piece the last bit together. For this e to the negative, so my little y of t, this e to the negative pi over s, it's outside my Laplace transform, so when I go here, I'm going to get a Heaviside of t minus my capital T being pi over 2, so this minus pi over 2, times the Laplace transform, so it'll be this whole thing. I'm just going to call this f of t, so I don't have to write it out 3 times. So this whole thing, but it's going to be evaluated at t minus pi over 2. Okay, so I just plug in the t minus pi over 2 into here, so my cosines then get shifted just like my sine did. So what's going to happen is these coefficients, the numbers a fourth and an eighth will flip. And I'll get to this minus from this one, u of t minus 5 pi over 2 times f of t minus 5 pi over 2. Yep. So we'll zoom out. That's the whole thing, right? Now you can simplify this, right? So these cosines, when I plug in this term, I'm going to pull up a negative out of here, and the sines, when I pull this term, I'm going to pull out a negative as well, right? Just trig identities, right? In general, this would be the form of the solution. And if you think about it, what's really happening is I'm going to have 0 for the input, which makes sense, right? If I have an unforced system with no initial conditions, it's not doing anything until I put a forcing term. So it'll be 0 until I hit we will go back to pad, pi over 2. And at this point, I now apply a forcing term, right? So now it's going to do this sine cosine thing. So this is going to grow linearly with respect to time, because the t here. So I'm going to get some oscillations. It'll do something, so something like this, caricature picture, until I hit wherever my 5 pi over 2 is, right? And once it hits here, then I turn off the forcing term, right? So the behavior should be different. For this system in particular, if I go back up to the original DE, there is no friction. So in this case, I should just get oscillations forever. So at this point, I'll have oscillations that weave back and forth, no growth, right? So the peaks and the valleys will stay the same. But here, I'll get this kind of growth term. So what I'll do is I'll actually plot this function, build the MATLAB code, show you what this guy looks like just to end the lecture. Okay, here I started code. I'm just going to finish doing this live so you can actually see this process in case some of you find it useful. So I just built a function handle for f. So that's what this first line does. So this just builds this guy. If I plug in numbers like f of 5, it'll tell me what that part of the function is at 5. I've built t in memory as like an array, so I have the data that I want to plot. And now I can just tell it to plot t. Here for the Heaviside function, MATLAB might have a Heaviside function, but I can just turn this on and off by just doing this, pi over 2. So if I say this is going to be 1 if t is bigger than pi over 2, so it's going to turn on just like the Heaviside function. Then I can just multiply this by f of the same point, so t minus pi over 2. Right? And MATLAB might have a function that makes this a little bit less ad hoc, but this works. So if I do this and plot it, and pull the plot over here so you can see, what I have is my function starts from 0 up to pi over 2, and let's plot some extra bits on here. I can plot the point pi over 2 for you. So I can do pi over 2 times the vector 1, 1, and I can do, so if I look at the time scale, I'll just have it go to 1.5. That seems decent. Minus 1, 1, oop, and multiplication, and let's make it a black line. Oops, and let's not do this. There we go. So plotting a black line there, so that's when things turn on, and when it's supposed to turn off is at 5 pi over 2. So I can plot a black line there, which I'll make a bit taller, 2, and I'll make the other one the same height as well. Right? Oops. This one and this line. Boom. Ah, that's the one where I messed up. Okay. There we go. So this is where it turns on, and I start forcing it. So vroom, vroom, and then I turn it off. It's going to be at one of the peaks because, well, I'm turning it off at 5 pi over 2, right? So just look at what sine looks like at that point, right? So then after that, I get these pulsating bits here. I said in theory these should be constant, and we can actually go figure out what that should be. So if I take my original function, oops, this was this part of the function, right? What I should get is that, where would I get the max? I can just do it this way. I'll just brute force the whole thing. I can take my entire function and I can say, go find the maximum value of it. Tells me what it is, and then I can plot those lines. So if I plot this at 0.57. If you wanted more accuracy, obviously you could not hard code it. Hashtag, these are not good programming practices here. So what I want to do is plot a line of that slope, so I can say that plus 0 times t, make it black. Actually, we'll make it red. Yeah, so there I get my top line, and I can plot the bottom line, right? So here you see it has the behavior I expect, and if I really want, I'll do that offline calculation real quick. Okay, if I found the right line, the line that goes from here to the peak should maybe be this. Yay, I can has math. And we can do the same thing just with a negative slope, which should just be that. Yeah. So here we can see the envelope of the linear growth with respect to time. It's not a perfect match because I'm literally just matching these points. You could actually compute what it should be for the top. But yeah, there we go. So we can turn these things on and off using our piecewise continuous functions, right? We can use piecewise continuous functions to model these turning things on and off. And mathematically, we can solve those problems by using the Heaviside function. And it's just a slight extension of what we've done before. You use the one rule that we introduced previously, the time shifting, to actually, well, first you write it of the right form. You use this to pull out your Heaviside functions. You compute some Laplace transforms. Then once you go compute these Laplace transforms, you multiply it by the transfer function. That's the thing where I multiplied through by this. Where did I do that here? Oh yeah, at the end. Where I multiply through by that to get this guy. Then you just take your inverse transforms. Again, since it's coming from a time shifting, when you do the inverse transform, you'll have another time shifting. So that's basically the Laplace method here in a nutshell. I will stop this video and go make your tutorial.